on the design and synthesis of metallayne and polymetallayne materials and study their structural property relationships of optoelectronic and catalytic application. She has published extensively in high-impact journals and received multiple awards for excellence in research, teaching, and scientific contribution. So, Dr. Balushi Rayya will present her talk, which entitled Exploring Structure Property Relationship in Metallayne and Polymetallayne for Advanced Optoelectronic Application. So the floor is yours, Professor Rayya.
Thank you very much. I'm Rayya Balushi. First of all, I'd like to thank the organizing committee for their efforts and in their communicating us and for organizing such wonderful conference. So my talk is about exploring structure property relationships in metallaynes and polymetallaynes, and we will be highlighting the photophysical properties and some of the optoelectronic applications. So let me first give you a brief introduction very quickly about my institution. So I came from Rayya University, and it is located in a small town which is called Ibra. It is in Oman. It is 150 kilometers from Muscat, the capital. And also I'd like to warmly invite all participants and attendees to our upcoming international conference on green and sustainable materials, which will be held at the university campus on the 13th to 14th of October. And it is a hybrid, free registration, and we will also offer publications in 2 indexed journals. You can just visit the website, and if you have any require any clarification or further information, please email me. So starting with our topic, so materials science deals with synthesis and chemical characterizations of new materials and forge the link between the synthetic and natural materials. We study them through physical measurements and theoretical studies. So broadly speaking, materials research it's just carried out on metal, ceramics, semiconductors, biomaterials, composites, and polymers. And we are mainly working in polymers and especially on conjugated polymers. And today in my presentation, I will be highlighting our recent work in 3 domains: organic polyynes, polymetallaynes, and metal organic framework. So this is the general structure of the polyynes and polymetallaynes. So, for example, here, which is shown in structure number 1, we have a purely organic system where we have a spacer groups. These are representing spacer groups, and they can be aromatic or heteroaromatic spacers, while for the polymetallaynes, we have also incorporated a metal, and it is a group 10 metals. Also, we can use 8 or 9 or even 11 metals, but mainly our work is in a platinum complex, in platinum, palladium, nickel, and I'll give some examples of copper complexes which synthesized and studied by our research team. L here is auxiliary ligands. It can be tertiary alkyl phosphines, and usually we use this in order to increase the solubility of our polymers. N is degree of polymerization. It can be 100 and so on. This type of materials, they have many features, and one of the important features is they are synthetic flexibility. For example, we can change the metal or the spacer group or even the auxiliary ligands. By changing one of these, we can also fine-tune the properties of the obtained materials. So we can sometimes, we only change the spacer group, and we got materials with different application, not only the similar application. It will change the properties too much, so even it will be a different application. This type of materials also, they are soluble in common solvents, and once they are soluble, of course, they are processable. We can cast them into thin films for characterization, such as in order to study, of course, their properties, such as photophysical studies. And they have high molecular weight and thermal stability, and they find many applications in optoelectronic. Due to their optoelectronic properties, we can they find applications in different type of like optoelectronic devices. So here are examples of a number of spacer groups which have been studied by us or by our other research groups. So mainly we change the spacer groups in order to fine-tune the properties. So for example, we can have a hetero-aromatic spacers like benzene, naphthalene, anthracene, or we can have a hetero-aromatic like thiophene, bipyrophene, or pyridine, and so on. So by having these different spacers, we found that we have different materials with different properties, as we'll see later. Now let me highlight why we add the heavy metal there in our materials. And by having a heavy metal like platinum in the backbone of our polymers, we found that if we were able to study or measure the phosphorescence, not only the fluorescence, because once we have a purely organic system, then we can measure all fluorescence. We don't have access to the emission from the triplet states. But by having this, then enters a heavy metal, then enters system processing can be measured, and so also we can, of course, measure the emission from triplet state. This type of materials, as I mentioned, they have many applications. They found applications in light, in liquid crystal displays, in light emitting diodes, in sensors, and in solar cells, as we can see here. This is our organic system, organic polymer, while these are platinum type materials. And usually in our work, we start for preparation of our polymers by designing and synthesizing our acetylide ligands. So we have the precursor, the salt, dibromide or diiodide, and we react them with the trimethylsilide to make the protected ligands, and this is a cross-coupling reaction, which of course it is very sensitive, and usually we face issues in the yield due to if we have any air there, then we will not be able to have a good yield, because we'll have a byproduct, which is the homocoupling. So we try our best to work in an inner system, and then we just proceed with the deprotected ligand. And once we have the deprotected ligand, which are not very stable, we directly, once we have this ligand, the terminal ligand, we react this with the platinum salt using copper iodide and the amine as a solvent in order to enhance this polycondensation reaction in 1:1 ratio between the platinum salt and the terminal ligand. As we know that polymers, they are big molecules, and we cannot, of course, characterize them fully especially by X-ray crystallography. So people, they tend to synthesize a model compound diene compound. These are building blocks for the polymers, and they are more crystalline than the polyions. So once we have an X-ray of the dimer, then we will be able to characterize the diene, and so we'll have a clear information about the polymer morphology, like bond angles, bond lengths, and so on. So this is an example of a crystal structure of one of the model compounds which I studied, and usually we support our experimental data by theoretical calculations, and here this is an example of the HOMO and LOMO. So of course, by having an information about the conjugation, since we have a conjugated system, then this will be giving us an information about the delocalization, and once we have a polymer with a big chain, then of course this polymerization, delocalization will be a larger chain, and so it will be, since we have more high extent of delocalization, then of course they will be better for the applications, of course, in optoelectronic. This is a study which was done by our group, and here we observed that by changing the spacer group only, without, of course, we have a platinum as a metal, we found that by moving from 31 spacer group to 34, there is a red shift in the properties, optical absorption and the emission properties, where we have the singlet at a lower energy. And this is by comparing the polymer with the dimer, we found that they have similar properties, and except now that for the polymer, the redshift is more because now the system is, of course, long chain, and from this we just came to know that they have similar properties, and thus it is good to have polymer as a dimer as a model compounds, and study their morphologies by reflecting, the properties of a dimer for the polymers. So what we did, we started with one of the spacer groups which we use is carbazole. And why carbazole? Carbazole, it's an electron-rich, and it has a planar conjugated structure, and without any substituents, it has a thermal stability up to 240, and also there's another property that it is can be functionalized with different units at nitrogen here position, which is 9th position, and the carbazole materials are well known as a blue emitters. So we thought that by incorporating this spacer group into our platinum polymer, then we will be having materials which are good for liquid light emitting diodes. So we started by synthesizing our materials, and we found that, of course, we here selected that we added our acetylide ligands through the 2,7 carbon 2 and carbon 7, which is somehow a linear structure. And also we compared this with the other ligands where the acetylide are connected through the 3-6 positions, and we found that by having more linear systems, the conjugation is more, as it is clear here that we will be having better conjugation in 2,7 compared to 3-6, where there is a hindrance in the conjugation. So this type of materials, just we came to a conclusion that we need just to work on this one in order to a little bit, of course, improve the properties so that they will be better than the available in the market. And a second system which we used is azobenzene. So azobenzene is photoresponsive chromophore, and it undergoes trans-cis photoisomerization, and by we thought that to have a different application, as I mentioned, that by changing only the spacer group, we will be having different applications. So we thought to have a photo switchable smart functional materials where it can be used as a photo switch. So here, these are the para and meta. So this is the first one. Here the meta, where it is a king, and this is the para. This is the polymer with the dimer. And we found that both ligands, this is of course the photoisomerization test, that both ligands displayed, which is the para and the meta, displayed photo-induced isomerization, transist isomerization, and this photoisomerization, it is more clear with the ligands than the dimer and the polymer, and this could be because of having this big molecule, big units, which is the platinum unit there, which might a little bit hinder the switch. So we extended this. As I received while I was working with this, we received a comment that maybe the issue is by having those N groups there in the azobenzene. So we changed them. Instead of having the azobenzene, we replaced them with stilbene. And what we found that similar observations that we still, yes, there is photoisomerization, but it is not as fast, so we couldn't get very good photo switch by having this platinum unit there. And even in the azobenzene, somehow the photoisomerization was somehow better, but they are, to some extent, they are similar. Then we try to improve the properties of our materials by incorporating a second metal. Means that we have that the spacer group. Now we just incorporated a metal as it is here. This is a spacer group. We already studied the bipyridine as a spacer group. Now we added, since we have this N there, then there is a possibility for combination. Okay. To having this rhenium. So we selected rhenium 1 unit in our material. So here that we prepared first the ligands, incorporated the rhenium unit, and then we added to this one the platinum. So to have a system like this. So here we are having two metals. So these are heterometallic systems, and what we observed that we have the properties, the photophysical properties are better by having more second metal, and we also, as it is clear here, we measured the photophysical properties as shown here. Here it is without and without rhenium, and the below data are with the rhenium. And as it is clear here that there is a shift, there is a red shift in the properties. So it indicates that the chelation of the bipyridine ligand produces a better photophysical properties. Why we say it's better, because once we have a red shift, then we'll be having a band gap, which is maybe it's less, so it is more useful for applications such as light emitting diodes or solar cell. So we tended, in order, of course, we are just working on improving the properties of our materials. So from the comprehensive literature review, we found that by having manganese, that manganese complexes, they are good as a catalyst. So we thought to replace the rhenium with manganese. And why we selected manganese? The manganese materials, they are low cost and they are available, so easy availability, and they are sustainable as they are good catalysts. The manganese complexes are good catalysts for the reduction of carbon dioxide. So we prepared our materials by having manganese 1 as a pendant group there. And this is our current work. We're still working on this. We already prepared our materials and we started studying the catalytic properties of this by doing electrochemistry studies, and it gives positive indications by converting the CO2 into useful materials like methanol. This is still ongoing, and still we didn't publish this work yet. As I mentioned that we can also change the metal. So here we also did studies, previous studies in having materials by using copper as the metal. So the materials undergo fissile oxidation under mild conditions, and we found that by changing only the copper, the salt, the copper salt, copper iodide to copper bromide and copper chloride, we have different morphologies. For example, with copper iodide, we have this cubic morphology, while by having copper chloride, the bromide, then we got the dibaric structures. The problem which we faced with these materials is that the presence of ferrocene humbled the processing of these materials and their applications, because we couldn't, especially in solar cells, because the materials were with less solubility. So we replaced the ferrocene with phenylphosphine groups with different phosphine ligands, and we found that the materials, they are very soluble, they have good solubility, so we could process them and characterize them, and we found that here, as it is clear in the slide, that we use different type of ligands and phosphine salts, and the copper complexes 7 to 10, where they are, of course, with different ligands displayed power conversion efficiency on the range of 0.15 to 1.56, where the complex 10 that contains this phosphine, which is the sulfonic phosphine, it is with the highest power conversion efficiency, which is 1.56. So this opens a window of further different copper complexes. We are also still working on new materials with copper salts. So in conclusion, metallaynes and polymetallaynes offer a tunable structure property relationships by we can fine-tune this by only changing the spacer or the metal or even that unit, and so we can support our experimental by the theoretical. Of course, I didn't highlight the theoretical studies here due to, of course, time limitation. So at the end, I'd like to thank the Ministry of Higher Education, Research and Innovation for funding, and of course, Sharqiya University for support, and also for internal grants funding. Also, I'd like to thank our collaborators from Sultan Qaboos University in Oman and also University of Bath. And of course, a special thank to my research team, Professor Khan, Dr. Haq, and also my students and the research assistants in my lab. Thank you very much, and I'll be very happy to answer your questions.